This will finish up this long sequence of videos about mappings in this particular example with z goes to z squared and complex numbers. I want to go back to this observation we had of what the pattern is. When we got this the standard grid, the rectangular grid over here, that went to this grid over here. Let me show you one of these things that this program can do. We can step through and see where everything goes. So these red lines where the horizontal coordinate is constant go to certain parabolas, and then the blue curves go to this other family of parabolas that seem to be always orthogonal. Okay, and we want to get to that, except we want to think if there's any exceptions, if there's anything weird about that. Okay, so here's the first question. I claim calculating the determinant of the matrix of derivatives is going to be instructive. Okay, and so we know that the matrix of derivatives, whoa, wrong part of the pen there. I've got these chisel tip pens and I forget sometimes. UV, that was equal to 2u minus 2v, 2v, 2u. And so the determinant of that guy is just going to be 4u squared plus 4v squared. That's 4 times u squared plus v squared. Well, that combination should be familiar. That is equal to 4r squared if we use polar coordinates over here. Okay. And what is one of the main uses of the determinant is figuring out if a matrix is invertible or not. Okay. So this matrix is going to be invertible, or it's going to fail to be invertible. So f prime not invertible. That's exactly when r equals 0. Oh, that's only at the origin. So everywhere but at the origin, we're going to have an invertible transformation. Okay, and that is very suggestive from the full computerized picture, which shows you that when I put in, let's look at the curves going through the origin. Okay, so I'm going to step this, so this is 0. So this says set the first coordinate to 0 and let the second coordinate vary. This says let, the second coordinate be 0 and let the first coordinate vary. So these are the axes. These are the curves that don't do what we kind of expected from the other ones. Everything else is this nice parabola, and they look like they're intersecting orthogonally. But when I look at how these two behave, at the origin they just turn around sharply. That's not a very nice thing to do. That's not a smooth curve. And they don't intersect nicely either. And all these nice things kind of bunch up and intersect badly at the origin. Even if we zoom in, let me see if we can zoom in. If we zoom in, we can still see it's kind of, there's weird stuff here. We don't get this nice picture anymore of the orthogonal intersections. Okay, so we'd like to explain that. Well, we've already gone a long way by looking at where this matrix is invertible or not. Okay, so it turns out that f prime being invertible is a very, very, very important nice condition to have. And this is where at the origin here, which corresponds to the origin here, because f of 0, 0 for this map happens to be 0, 0. For other maps it's not necessarily. But the origin on the input and on the output side is really a bad point. Now this is a very general thing, that asking whether the derivative matrix of derivatives is invertible or not turns out to be very, very general, and we'll talk a little bit more about that. For this particular map, though, there's this nice fact that as long as you aren't at such a point, as long as the matrix is invertible, that you get this fact that we've already observed, that the u and v grid curves, the images of the curves, these parabolas, look like they intersect orthogonally everywhere. So let's do that. So let's go ahead and say, let's suppose u and v is not at the origin. And then we'll analyze the origin separately. Okay, if they're not at the origin, then f prime of uv, I'm just going to write it out one more time, 2u minus 2v, 2v, 2u. Okay. Well, what did we know? The columns of these guys were these velocity vectors. And so how do we show that two curves are orthogonal? the curves are going to be orthogonal if and only if their velocities are orthogonal, or if and only if the columns of this derivative matrix are orthogonal, and that's going to be if the dot product equals 0. Okay, well, the dot product's really easy to take. The dot product of the columns is just minus 4uv plus 4uv equals 0. Check. So let's also look at what happens when u and v is not at the origin. This is not the 0 vector, and this is not the 0 vector. One really stupid way for a vector to be orthogonal to something, although it's important to use it as a special case, is when it's the 0 vector. But if we're not at the origin, then it happens to be that neither of these guys is the 0 vector, and they're sort of meaningfully orthogonal, not just trivially orthogonal. And that's exactly confirming this picture. Now, if we are at the origin, switch back to column vectors. Ooh, I shouldn't have used row vectors. Oh well. Okay. If we are at the origin, then not only is this matrix singular, it's actually the 0 matrix. That's a really profound way to be a singular or non-invertible matrix. And so basically it says that if I walk away from the origin a little bit, in terms of the first derivative approximation, the linear approximation of this function, I don't go anywhere. Now, I'm not really not going anywhere, but in terms of just tangent approximations, velocities, and things like that, I'm having a hard time getting myself going. If the bug walks over here, its image bug is just going to stay there to first order approximation. And so I'm not going to get these tangent vectors at all. And so it's very likely that I'm going to get a weird picture. And that's exactly what we saw in the computer. Okay? So it's only at the origin that we get something weird. Otherwise, we get this dot product being 0, and we get this lovely picture that because these curves were orthogonal, these curves all end up being orthogonal as well. Now, that is something that's special to this kind of map that turns out to come from complex numbers. But the general lesson here is look at the matrix of derivatives, look at the geometric information, look at where it's invertible, and then see if you want to get any other special geometric information out of it. That's it.